Okay, in this segment, we're going to start a series of videos that we're basically going to walk through the design of an edge-triggered D flip-flop that can be composed into a very nice shift register. And so this is both potentially a useful thing for you to consider using in your projects in case you need something to store some digital state. And it's also kind of a nice sort of relatively simple circuit that we can use to practice some of the things we've been talking about, like layout-driven schematics and digital gate design and things like that. So we're going to be looking at a static edge-triggered D flip-flop design. Okay, so you may recall from our discussion in circuits, one approach to doing this sort of thing is to take what's called a level-sensitive latch, D latch in particular, and that would be typically represented kind of at a slightly higher level than the gate level by something like D, Q, and clock signal phi. And when phi equals 1, D gets propagated to Q. When phi is 0, Q holds its state. Okay, so it's kind of an edge-triggered, or rather a level-sensitive latch. And in circuits we talked about how we could take two of these and make an edge-triggered flip-flop out of them. And we can do that by taking two of these, say DQ and the clock, DQ and the clock. And we basically feed the input into the first one, and we feed, so this is the D input, this is the Q output of the overall thing. Say we feed phi in here, and then we invert the clock into the second one. And the basic idea is that when phi is high, this first latch is sampling. Okay, so so let's say this is the clock signal. We'll call this latch 1 and 2. So in this phase, 1 samples and 2 holds. In this phase, 2 samples and 1 holds. So what that means is that when phi is high, this latch is sampling and propagating its D input to its Q output immediately. But as soon as phi falls, this latch becomes opaque and no longer is sampling its input and maintains a steady value for latch 2 to sample. And then on the falling edge of phi, D gets propagated to Q at the output, and so for phi low, this is maintaining a constant value, the final value that was sampled during the phi high phase. And so in effect, this becomes a falling edge triggered flip-flop. Because what happens is, effectively, D gets propagated to Q when phi goes low. And when phi, otherwise, during the clock phase, nothing happens to the output. Okay, that's in theory what happens. So if we wanted to, we can rearrange this very easily to make a rising edge triggered flip-flop. By simply putting the inverted clock into the first phase, or the first latch. So I mentioned in circuits probably that this particular arrangement of two level-sensitive latches to make an edge-triggered flip-flop has a rather unfortunate name that's politically incorrect at this point. So let's not talk about that and its references to undesirable practices. We might call this a leader-follower arrangement, where the first latch is the leader and the second latch is the follower. And that first latch holding its state for the follower latch to follow and create a nice stable input for the follower latch is kind of how it works. So we could call this the leader latch. We can call this the follower latch. Okay, so if we want to make a rising edge triggered flip-flop, we can simply take our two latches, DQ, DQ, and put phi bar in here and phi into the second stage. So the first latch is sampling when phi is low, and as soon as phi goes high, the first latch closes and becomes opaque, and the second latch then samples that final value that D had when phi went high. So that's kind of how this works. The classic issue with, or the classic potential issue with this type of sort of leader-follower arrangement happens when, potentially when there's enough delay through that inverter that both latches are transparent for a very short amount of time. Okay, so let's imagine our rising edge triggered, or let's imagine our falling edge triggered version, which I guess I shouldn't erase if I'm going to talk about it. Let me erase it anyway. So let's put our falling edge triggered flip-flop here, so we get DQ. DQ. And let's imagine a situation where we have phi, maybe like this, something like that. And let's imagine that that inverter has some appreciable delay, and phi bar winds up being something like this. Right? So here's a period that's just a delayed version of phi. It's not what I'm looking for. I'm looking for phi bar, and I'm looking for delaying the complement. That's what I'm looking for. So phi bar might look like this. Right, so there might be some finite period of time where we have, phi has gone high, but phi bar has not gone low yet. And during this brief period of time, of overlap between phi bar and phi both being high, both of these latches are transparent. And what can happen is that D flows through to Q during this overlap. And that's called flow through. And that's a potential problem with this arrangement. So one classic solution to this problem is, instead of having a clock and a local complement of the clock, or worse yet, the clock and its complement distributed, let's say from the edge of a long shift register or something like that, would be to use a two-phase non-overlapping clock. And the way that that works is that we have two clock phases that we distribute. Say phi 1 and phi 2. And phi 1 and phi 2 kind of look like phi and phi bar, except we're very intentional to make sure that phi 1 and phi 2 do not have this potential overlap. So phi 1 and phi 2 might look something like this. Let's say phi 1 is low, goes high, goes low, and phi 2 is high, goes low before phi 1 goes high, and then phi 1 goes low before phi 2 goes high. And so this is, there's a definite period of non-overlap between the high times of the two clocks. And there are ways to generate signals like this. Of course, one issue that arises immediately is if you're distributing these clock phases over any appreciable length on the chip, there's always a chance that you can get skew between the two clock phases if the two clock lines may have different kinds of meandering paths or may have different loads on them or something like that. And so you have to be very careful about clock skew when you do this kind of thing. Instead, with this design that we're going to work through, what we're going to do is to distribute a single clock phase and have our two level sensitive latches be slightly different designs. Okay, so instead of doing this and have to worry about clock skew, what we're going to do is we're going to make the first latch what we're going to call a phi latch, and the second latch a phi bar latch. So we're going to make two versions of our level sensitive latch. We're going to call this one a phi latch, and we're going to call this one a phi bar latch. So, and we're going to distribute a single clock phase to both latches. So the phi latch is transparent when phi is 1, and the phi bar latch is transparent when phi equals 0. Okay, it turns out that we can do that fairly simply. Once we design our phi latch, we just take the upside down version of that latch, and that becomes our phi bar latch. Okay, so the phi bar latch is the upside down version of the phi latch. Okay, we'll see what that means. So let's talk about the design of a level sensitive D latch. So if you open up any old textbook on digital logic design, the classic D latch would be, well, clocked D latch would be a pair of cross-coupled NOR gates, like so. And that would be fed by basically two AND gates. And so this would be the clock. And this would be D, let's say, and D bar. And the idea here is that when phi is low, these AND gates will present just zeros here to the set and reset inputs to the D, well, to this SR latch, effectively. But then when phi is high, then one of these two AND gate outputs will be high, depending on whether D is high or low, and that will set or reset the output of this latch. Okay, and so let's work out which of these is Q and which is Q bar. Okay, so let's see here. I think that makes this Q and this Q bar. Let's just check that out. So if we have A, B, and A nor B, 0, 1, rather 0, 0, 0, 1, 1, 0, 1, 1. And so not or would be 1, 0, 0, 0. And so if, let's say this is the A and this is B, right, so when A is high, then the output here goes low regardless of the value of B. And so that's the behavior we want, because Q would be then 1. Because this would be 0, and D bar would be 0 if D is 1. And so this would be a 0, 0, and that row makes this a 1. So this is the correct labeling of the outputs. Okay. Now, we could just work with NOR gates and NAND gates, and we can do some reshuffling here, and we could come up with an implementation of this that involves like 4 NAND gates. But rather than doing that, since this is a course about transistor-level circuit design, we can design a fairly monolithic gate that actually has 3 inputs in order to design our level-sensitive latch. So we're going to do that. Right, we're VLSI designers in this class, not standard cell designers. So here, Q bar, or rather let's say Q, Q would be equal to Q bar NOR together with D phi. Right? So looking at Q, that's the output of a NOR gate, so we've got a 2-input NOR, and 1 input to that NOR gate is Q bar, and the other input is actually D bar and phi. Okay. Of course, we can use De Morgan's law and rewrite this as Q and D bar phi NANDed together. And that's, of course, equal to, applying De Morgan's other law here, that would be Q ANDed in with D or phi bar. All right, so there's a number of ways we can write this. Not sure which will be the best way to think about it. I think we're going to think about going with this form here. Okay. Well, sure, why not? So let's think about synthesizing the pull-up network for this. All right, so we're going to have two things in series, and then we're going to have one of the two things in series is the Q transistor. All right, so we have something like a Q bar. It's not right. I keep saying Q and I write phi, and I say phi and I write Q. So this is going to be Q. And that'll have to be Q bar because of the bubble. It's going to be in series with phi bar. Or no, actually phi. All right, we have a complement on the phi. That's good. So that means it's just phi. And then over here we have D. Okay, so that should be the pull-up. And we can synthesize the pull-down by just taking the conduction complement of this thing. So we're going to have two things in parallel. There's the Q bar. I almost did it again. Q bar. And off to the side, so that corresponds to this, and that's going to be in parallel with two things in series. So we've got a phi for this, and then a D bar that goes to ground. and this would be Q. Okay, so this gate will implement basically this NOR gate and this AND gate. So the functionality of these two pieces is in this gate. Okay, so now I'm going to erase, just fix this. So these are all together here, so that's good. We can just kind of tie these gates together. That's convenient. And this should be Q bar. Now, of course, the other half of the circuit is symmetric, so the Q bar is the output of a very similar gate here, because obviously it's the same functionality, right? It's just that it has a D, where we have a D bar here. Right, so we have to feed D bar in to complement, to compensate for the bubble here on the PMOS. So anyway, so we have the same kind of gate, except where we had D bar, we put D, and in place of where we have Q bar, we put Q. Right? So Q appears here, D instead of D bar and Q bar. And so we can kind of draw this in a symmetric fashion to get the whole thing. Okay, so it's going to look something like I'm just going to kind of mirror image this here. So we've got okay, a little hiccup there. So here we're going to have a phi. We have our parallel connection here. So D goes here. Maybe I'll move over here. And then we've got our two series transistors down here. There's phi, and there's D. And so this is Q bar, and that Q bar input goes there. And then we have here Q as an input to this guy. So this is the phi latch. All right, so if you imagine phi being low, let's imagine phi being low. Well, this is off. This is off. This is on. This is on. It's this one that's on. Right, so with phi being off, this D transistor and this D bar transistor can't do anything to pull down on either side of this pair of cross-coupled inverters. And with these two transistors on, you're pinning the power supply of these sources here up to VDD instead of potentially cutting them off depending on what D is doing. So regardless of what D and D bar are doing, these two clock transistors are holding the sources of these cross-coupled inverters, the bistable element here at the core, up to VDD. Okay, so it's going to maintain its state. Whatever Q and Q bar are, it's holding. Okay? So this is the opaque phase. When phi is high, well then, we flip these clock transistors around. And what we have effectively, if you think about it, so if you imagine this is like a short circuit and this is like an open circuit, you've got the D transistor in parallel with the feedback from Q, right? So those two transistors are in parallel in the pull down. And then we've got the D and the Q transistors in the pull-up network through the only potential path in series with each other. And so that means that these four transistors form a NOR gate. Okay, so effectively, the two halves of this latch are a pair of cross-coupled NOR gates, and that would give you kind of a classic set-reset latch behavior during the phi high phase. And so that means that since D and D bar are complementary to each other, then this is going to be like a transparent D latch with no writability problem. And so this is the transparent phase of operation. Okay, so this is the first half of our D flip-flop. And the second half is basically just flipping this upside down. Okay, so the way that you flip something upside down is you make all the NMOS transistors PMOS transistors, you make all the PMOS transistors NMOS transistors, and you literally flip the whole schematic upside down. So these points up here become ground. These two transistors become NMOS transistors down here in parallel. They'd be in series with another NMOS transistor, and that would be the pull-down network with half the gate. And then this structure would be flipped up. These 2 points would be VDD connections. You'd have 2 paths in parallel in the pull-up network. These 2 transistors would be in series in parallel with that single transistor there. Okay, and we'll draw that. But in the next segment, we're going to work on making this into a warping the schematic into a layout-driven schematic. And then we'll just take the upside-down version of the layout-driven schematic. Okay? So that's where we're going next. Thanks for watching.